BocaPhysics series on electromagnetism. In today's lecture, I'm going to be discussing linear isotropic dielectrics. So what do I mean by that? Polarization is a function of the electric field. The electric field is what gives rise to the polarization. This is called a constitutive relation. I can write out an expression explicitly in terms of the electric field. So the polarization is proportional to the electric field, and we've got our constant here, the permittivity of free space. And now there's this new quantity, which we'll call the electric susceptibility. This depends on whatever material you have, and it also depends, generally speaking, on the applied electric field. However, for many substances, the electric susceptibility is independent of the field as long as the field is not too great. So susceptibility for many substances is independent of the electric field as long as the field is not too great. That is what I mean by linear. So if it's no longer dependent on the electric field, I can drop out that dependence on either. And what do I mean by isotropic? Well, isotropic means that your polarizations the same way as the electric field. A lot of substances are isotropic, fluids, for instance, amorphous solids. However, if you consider crystals, crystals are easier to polarize in certain directions than other directions. And in that case, you don't just have a number for the susceptibility, you actually have a tensor. Susceptibility tensor has 9 elements, and it looks like this. This is undergraduate electromagnetism, though, so we don't deal with anisotropic materials. You'll leave that for graduate electrical engineers. Okay? So if you have a linear isotropic dielectric, that means that the susceptibility is independent of the electric field as long as the field is not too great. And also the polarization is pointing the same way as the electric field. So essentially we have this relation. And this susceptibility is just a constant scalar. Okay, so I want to flesh this out a little bit more. And let's recall the displacement here. Displacement, which we introduced in yesterday's lecture, is defined as the permittivity of free space times the electric field plus the polarization. We'll place insert this expression in here. As it turns out, there's convenient to introduce yet another quantity, and we'll call that K, and that's the dielectric constant. Before I proceed any further, I just want to make a quick comment about the notation I'm using. This is consistent with Griffith's notation. He defines polarization as the permittivity of free space times the susceptibility times the electric field. If you happen to look at an older textbook, for instance by Wright, you'll see that the permittivity of free space is actually absorbed into the susceptibility. So the expression looks like this. It's just not really any big deal, but it's just if you happen to go from textbook to textbook, you run across notation like this, just be aware that people define things a little differently. Okay, now this we're calling the dielectric constant K. And this is the permittivity of the dielectric medium, and that's equal to the dielectric constant times the permittivity of free space. Now, another comment about notation here. If you happen to be using Griffith's textbook, note that he doesn't call it dielectric constant, he calls it the relative permittivity. And it means exactly the same thing. I'm going to stick with K. The reason why is basically old habits or old habits, okay? And it's used by Wright and a lot of general physics textbooks, so I'll stick with K, and just be aware that Griffiths use epsilon R. So we should have an idea of what K, what kinds of values K can have. So let me first consider a vacuum. K is just equal to 1. Well, that makes sense. Our results should go back to what they were. If we don't have any dielectric medium there, we just got a vacuum. Looking at this relation, if K is equal to 1, well, you can conclude that susceptibility in that case is just going to be equal to 0. Well, susceptibility is 0, then you don't have any polarization. Well, that's consistent because, after all, if you're talking about a vacuum, there's nothing there to polarize. So P is going to be equal to 0. Okay? So that's the vacuum. If considering air, K is equal to 1.00054, and that, of course, depends on what the temperature is, how much water vapor is in the air, and so forth. Basically on environmental conditions. So you'll see a little bit of difference in this final digit here. Water has a dielectric constant of 80, and again, it depends on the temperature of the water and other such external properties. And it's also useful to think that, well, if you're talking about a conductor, K is infinite. Okay? So now that I've defined what linear isotropic dielectric is, let me work a couple of examples. In the previous lecture, we talked about Gauss's law, and we applied it to a couple of systems. And one of those systems was a very long charged wire. bears line charge density lambda. And that very long charge wire is surrounded by a dielectric sheath. So because the system has the requisite symmetry to apply Gauss's law, we concluded that the displacement everywhere, both inside and outside the sheath, was just equal to lambda over 2 pi s and in the radial direction. Outside of the sheath, the electric field is just equal to lambda over 2 pi epsilon naught over s, also in the radial direction. Now, because I didn't tell you what the polarization was, that's as far as you could go, because you can use Gauss's law to determine the displacement. You have to know what the polarization is, too, to figure out what the electric field was. But that information wasn't given. So as far as what was going on inside, the most you could say is, well, this is what the displacement was. Okay? But now I'm going to go ahead and tell you what that sheath is made out of, or give you a quantity that characterizes it. Let's say that it has dielectric constant K. So therefore, outside, or rather inside, the electric field is equal to the displacement over the permittivity of the material. And permittivity of the material is just equal to the dielectric constant times epsilon naught. So therefore, the electric field inside the sheath is equal to lambda over 2 pi epsilon naught K times S in the radial direction. So you see the effect of the dielectric medium gives rise to a kind of shielding of the charge. The effect of shielding can be seen, I think, a little bit better in the next problem that I'll show you right now. Let's suppose that we have a linear isotropic dielectric sphere. Of radius r. And let's suppose at the center of that sphere we have a charge q. And that is free charge or embedded charge, okay? And let's suppose that this dielectric sphere is characterized by a dielectric constant, K. I want to figure out the usual. I want to figure out what's the electric field, and along the way I want to figure out, well, what the polarization is, what the bound surface charge density is, and what the volume charge density is, and so forth. Okay, so where do I begin? Well, since we've got a system that presents the requisite symmetry, I can make use of Gauss's law. And you know the drill. If you've got a sphere, you want to choose a Gaussian surface that's also a sphere and that's concentric with the physical system in question. So therefore, I know that the displacement is going to be constant over that surface, so I can just pull d out and I'll just have 4 pi r squared times d is equal to the free charge, which is just little q, and therefore the displacement is equal to q over 4 pi r squared in the radial direction. Now to figure out what the electric field is, because we are just dealing with linear isotropic dielectrics, I can make use of this relation. and that's inside the sphere. We have Q over 4 pi epsilon naught k r squared in the r direction. So the electric field looks like the field just to a point charge. However, you have this factor k in the denominator, and that serves to reduce the magnitude of the electric field. So there's a shielding going on. I'm going to flush that shielding out business a little bit more. So let's look at the polarization. Polarization I can just figure out using this expression here is equal to D minus epsilon naught times E. Okay. So again, in the radial direction, we'll figure out what the bound surface charge density is. Interesting what's popping up on the surface of the sphere. So that's polarization dot normal, evaluated the surface of the sphere. And in this problem, the normal direction to the sphere is just in the radial direction. So therefore, we wind up with Q over 4 pi radius of the sphere squared times 1 minus 1 over k. Now let's suppose I want to figure out what the bound volume charge density is. Well, that's minus the divergence of P. And if you recall what the divergence is, it's basically you're having 1 over r squared partial derivative with respect to r of r squared times the earth component. Well, if you do that, say, well, gee, it's going to vanish everywhere. And it does vanish almost everywhere except at the origin. So essentially, you were going to have a delta function. So this is equal to minus k times 1 minus 1 over k times the delta function. So it vanishes everywhere except at the origin. I've got a certain amount of bound charge appearing on the surface of the sphere. So on the surface, this is just a constant, so basically I can just multiply this by the surface area of the sphere. It's just going to be Q times 1 minus 1 over K. At the center, I can integrate that over the volume, and I'm going to wind up with minus Q times 1 minus 1 over K. So you see the total bound charge, this plus this, vanishes exactly as it must. Another way to look at this problem is to think of, well, let's consider the charge Q, the physical, free charge Q, and let's consider the bound charge that's right there as well. I'm going to add those up, okay? So I've got charge Q minus Q times 1 minus 1 over K. So I have Q minus Q, that drops out, and then I have a Q over K term. So you kind of understand that the effect of this polarization, or the effect of this dielectric medium, is to provide a shielding. So basically, I've got my charge Q, but it's reduced by a factor of K, the constant which characterizes the material that surrounds it. Okay? So let's do one more problem. Let's suppose that I have metal conductor connecting a sphere of radius Ra. And that is surrounded by a dielectric shell of radius Rb. Well, you know what we're going to figure out here, of course. We're going to find out what the electric field is everywhere. And along the way, I'll figure out what the polarization is and what the bound surface charge density is and bound volume charge density. Let's suppose too that this metal conducting sphere has a free charge of Q on the surface. So I want to figure out the electric field inside the metal conducting sphere. Well, this problem presents the requisite symmetry, so I can once again apply Gauss's law for dielectrics. And you know the drill. If you've got a spherical system, you choose a spherical Gaussian surface that is concentric with the system in question. So therefore, you wind up with 4 pi r squared times d is equal to q. Oops, and I should say this is actually going to be in this region. So that's d is equal to q over 4 pi r squared in the radial direction. This expression also holds outside the dielectric shell. Inside the sphere, metal conductor, the displacement vanishes. Why? Because there's no charge there. And the electric field equals 0 there as well. There's nothing, there's no free charge inside a metal conducting sphere, and there is no polarized material either, so electric field vanishes. In this region, the electric field is simply equal to Q over 4 pi epsilon naught r squared in the radial direction. So outside the dielectric shell. Inside the shell itself, however, the electric field is equal to essentially the field just due to a point charge, however, reduced by a factor of k. Now you can see the limit if the shell were just a vacuum. This would just reduce to the expression for the electric field due to a point charge in a vacuum. And as k gets very, very large, well, that's going to go to 0, which is as it should be. Okay, so those are the electric fields. The other thing I might want to figure out is what's the potential? And if you know what the electric field is, potential can be calculated by this expression minus the line integral from some reference point to some point r. Now, I want to figure out what the potential is at the center of a sphere with respect to infinity. So, first leg is going to go from infinity up to the outside radius of the dielectric shell, and the electric field there is equal to Q over 4 pi epsilon naught r squared dr. I'm next going to integrate from the outside radius of the shell to the metal conductor, so from Rb to Ra. So now we get a factor of k to contend with there. And the last region of space, we're going to go from the radius of the metal cylinder, or sorry, metal sphere to the center, and the electric field vanishes here. So that last term contributes nothing. if I do the math here, my first term contributes Q over 4 pi epsilon naught RB plus Q over 4 pi epsilon naught KRA minus Q over 4 pi epsilon naught KRB. And that's the potential of the center of the sphere, at the center of the sphere, with respect to infinity. Okay? Now just for the heck of it, let's calculate the polarization. That's equal to D minus epsilon naught E. And this, of course, is inside the shell. Outside the shell, the polarization vanishes. This is Q over 4 pi r squared times 1 minus 1 over k in the radial direction. Well, the bound volume charge density in this case just equals 0, right? And we don't have any delta function because we're evaluating this divergence in this region right here, from R is equal to R sub A up to R is equal to R sub B. So the bound volume charge density in that region vanishes. Now the surface charge density does not. On the inside surface, we have polarization down to the normal. So that'll be Q over 4 pi RA squared times 1 minus 1 over k. And there's a minus sign there, and the minus sign is because normal, in that case, is pointing inwards. At the outside surface of the shell, we have Q over 4 pi RB squared, 1 minus 1 over k. So you've got bound surface charge density in this case, however the bound volume charge density is equal to 0. Okay? And that concludes today's lecture.